Okay, so this is my Unit 2 Mastery project for FRQ 2. So, here's the situation. There is Block A with a mass of 4 big M, and Block B with a mass of just M. And they tell us that it's an ideal pulley, so the pulley is not gonna affect anything in the problem, and no friction. So here's question A. Okay, so pretty much they ask us to draw a free body diagram of block A and block B. So let's draw this. So there's this block A, and then there's string attached to it, pulley. There's theta right here, and then there's block B, mass 4M, and this is mass M. Okay, so for question A, or part A, they give us this dashed circle and then undashed circle. This would be block A. So it's really slanted, but they tell us that there's a string right here that's attached to A, and there's this thing that is pulling on block A. So we would start with, if this is the ground, I guess, and there's theta. So gravity would still be pushing downwards, and we would not annotate that, but name that force, this downward force, as its mass times its gravity, which its mass is 4m, and that's gravity. It's going, this block A is going this way, downwards, at this magnitude, because the block has mass, and also plus gravity. Yeah. And gravity is also pushing it this downwards motion, and the block also has a normal force, and this block also has a tension that's pulling on block A towards this direction. And as for block B, there's that they give us right here. And really the only things that are acting, or forces acting on block B, is just the tension that's pulling this block, which is tension, and then there's its downward force, which is its mass, which is just M, times its its gravity. Yeah. So this is part A of FRQ 2. Oh wait, I probably shouldn't do that. Next question. Part B asks us to create an expression for the acceleration of, that. So we're gonna have to use our free body diagrams that we created in part A to do this next part. So, alright. So we would always start with our force statements, F equals ma. Let's do the force statement for specifically block A first. So let me label that A. Okay, so technically, if you were to, I don't know if the word is resolved, but like, if turn this slantedly, and and make this our x-axis and this our y-axis, then the force of mg, force of mg would be, I guess, mgx, let's say, and mgy, yeah, towards this direction. That's a bad arrow, but okay, yeah. And oh, what the? Wait, give me 1 second. Okay. So, yeah. Anyway. And then because we're trying to find the acceleration of the blocks, there's no like y acceleration in block A, so we should completely ignore the vertical vectors, I guess, yeah. And yeah, so we're only focusing on the horizontal vector of block A, yeah. So because block A is going that way, there's an acceleration, and there's no friction, so it's not, there's nothing like, there's no force that's pulling block A that way. So it would be mgx plus t is equal to whatever the mass of block A was, which is 4m, and times the acceleration, which is what we're trying to find. That's literally it. And because we probably wouldn't want to have it as just simply mgx, and they did tell us there's a theta right here, and using simple geometry, think of this as one triangle, and because there's a 90-degree angle, there's 90, and there's theta, theta right here. This angle would be this and this. Wait, 180 minus this and this, which is that, which is also this, which means that this is theta. I know that reasoning is really like confusing, but it makes sense to me. So yeah. Continuing. Continue as in like, oh, this is mgx, so if this is theta, and this line right here is still 4mg, it's the same line, then sine is equal to opposite over hypotenuse, so sine of theta would equal to mgx over 4mg. And multiply that over, and you would just get 4mg sine theta plus t is equal to 4m a. There. Yeah, that's, yeah. And then there's b, which you would also start with f equals ma. And there's literally no horizontal vector, so we can only really do this vertical f vector for the block A and block B. So because it's pulling down that way, it would be its downward force minus the tension that's pulling it the other way, which is equal to big M, because it's, like as we said earlier, block B, the mass of block B is just big M. So acceleration there. And then when you combine these together, you would get something like this: 4mg sine plus t plus mg minus t is equal to ma plus 4ma. Combine these two, 5ma is equal to, and there, they cancel each other out, and we'd be 4mg sine theta plus mg. Yeah, and because everything here has m's, you can get those out, and you'd be left with 4 sine plus g, 4 sine, 4g there is equal to 5a. And then a would just equal to 4g sine plus g all divided by 5. That's your answer. And if you want to like take out the g, put it to the side, then that's fine. But this is the answer for how the expression for the acceleration. Yeah, there. So on to the next part, which is C, which arguably is kind of the hardest part, I think. Okay, so they give you this graph, okay? And they're asking you to find or graph the net force magnitude of the blocks at a certain angle, which the angle, let me move to the side. Okay, the angle, okay, so let me just redraw the thing. This is the angle that they're changing, and this is the block A. Oh, that's a bad block, but block B. Okay, so what it's asking you to do is graph the net force magnitude of these, I guess, magnitudes at certain like angles of theta. So what it's saying is when theta is 0, which is this, it would literally just look like this. And when theta is equal to 90, it would literally just be whatever this is, and this. Okay, so what's the starting point and what's the end point or of this graph that they give you? Which let me redraw right here. Yeah, 0, 9, 90 degrees, as in, and then this is just mg, 2 mg, 3, 4, and 5. Yeah, mg. Okay, there. So, let's explain it this way. Okay, so block B wants to move A this way, so just that's block B's magnitude. However, there's a tension right here. There's a tension that's right here that is pulling it like this way ish, and therefore in this graph right here, block A is moving this way at a net magnitude of block B's magnitude, which is just mg, minus the tension of the string. Which is why, if let's say if this much is the tension, or I guess no, if tension is this much magnitude of force, I guess, then it would start right here. Block A's graph would start right here. Block B's graph is just the only thing that's pulling up on block B is the tension. So block B would start right here. And because when when it's at 90 degrees, both objects, both blocks, are literally just in free fall. So both blocks cannot go downwards any faster than its like downwards magnitude if there was no like additional force that is acting on it. So it's just in free fall. So block A's like graph would just end at whatever block A's downward force magnitude is. Same with block B. So this is A, this is B. Okay. So I guess on to part C. Part D. Oh crap. Part D. So they're asking if there was no string and there was no block B. So describe how the graph would change, which is this graph right here. So for part D, let's draw the diagram again. Let's say if block A is right here. There's no string and there's no block B. It's just sitting there. So obviously its initial starting point, I guess, would not change. Would change actually. It would change because there's no tension pulling on it. There's no mg that's pulling on it. It's just standing there. It would literally just be 0. It would start at 0. So that would change, but when it's at 90 degrees and A is right here, it'd still be in free fall either way. So the end behavior of the graph would not change for block A because it's literally just in free fall. There's no tension, and there's no tension of the string that's pulling it downwards, even if there was a string or not. That's a bad explanation, but either way, even if there was no string on block B, which is in this case right here, both block A's are still in free fall, and the only downward force that is pulling block A downwards in both situations is just 4mg. That's it. It doesn't matter if there was a string or not. So the end of the graph would not change. However, the beginning will, because there's no string and there's no block B, so it can't move towards this way. The only force that's pulling it, I guess, there's no force that's pulling it horizontally, but in this case there is, which is why its starting point would change or be different. So that's my explanation.